Welcome to this lecture on Riemann integration. Today, we are going to explore a fascinating geometric problem: how to find the exact length of a bending, twisting curve. Imagine trying to measure a winding river on a map without a flexible string. How do we do it? We will use the power of calculus to turn rough approximations into perfect measurements. Let us dive in. Now that we know our goal, let us understand the core idea behind arc length. Why does this matter? In the real world, very few things are perfectly straight. To measure a curve, we imagine breaking it down into many tiny straight line segments. We can easily measure straight lines. For this to work mathematically, the curve must be what we call rectifiable. This simply means it is completely smooth without any sudden jumps or sharp jagged corners. We guarantee this smoothness by requiring the function to have a continuous first derivative. As we make our straight segments shorter and more numerous, our approximation gets closer to the true length. Before we look at the formula, let us visualize this microscopic approximation. What you are seeing here is a smooth curve plotted on an xy plane. Notice the zoomed-in section? When we look closely enough at a tiny piece of the curve, it looks almost like a straight line. We can draw a tiny right-angle triangle around it. The horizontal base represents a small change in the x direction, and the vertical height represents a small change in the y direction. The slanted hypotenuse is our straight line approximation of the curve's length. This simple geometric triangle is the secret to measuring any curve. This visual intuition leads us directly to our main formula. Conceptually, this integral is just the sum of an infinite number of those tiny hypotenuses we just saw. Let us break down the symbols. The capital L stands for the exact total arc length. The integral sign tells us to continuously accumulate these tiny lengths from our starting point A to our ending point B. Inside the square root, we have 1 plus the squared derivative of our function. The derivative represents the slope of the curve. Notice that as the slope gets steeper, the value inside the square root grows, which correctly calculates a longer distance traveled. Now that we have our formula, let us test it on something simple, a straight line. We want to find the length of the line y equals 2x between x equals 0 and x equals 3. We already know how to find this using basic geometry, but let us see if our calculus formula works. First, we find the derivative of our function, which is simply 2. This constant slope makes sense for a straight line. Next, we substitute this derivative into our arc length formula, setting our lower limit to 0 and our upper limit to 3. Continuing with our calculation, we simplify the expression inside the integral. Squaring the slope gives us 4 and adding 1 gives us the square root of 5. Because this is just a constant number, finding the antiderivative is incredibly easy. We simply multiply the constant by our variable x. Finally, we evaluate this from 0 to 3. Substituting the upper limit gives us 3 times the square root of 5 and the 0 lower limit vanishes. Our final answer is 3 root 5 units. This perfectly matches the standard Pythagorean distance formula, proving our calculus method works flawlessly. Let us tackle a more complex problem where basic geometry cannot help us. We need to find the exact length of a true curve defined by y equals 2/3 x to the power of 3 halves from x equals 0 to 3. Our strategy remains the same. We begin by finding the derivative using the standard power rule. We bring the exponent down to multiply with the coefficient and subtract 1 from the power. The fractions cancel out beautifully, leaving us with x to the power of 1/2, which is exactly equivalent to the square root of x. Moving forward, we take our simplified derivative and substitute it directly into the arc length formula. Notice what happens when we square the square root of x. The two operations cancel each other out entirely, leaving just the variable x behind. This transforms a messy expression into a very clean integral of the square root of 1 plus x. To integrate this, we treat 1 plus x as a single unit and apply the reverse power rule. We add 1 to the exponent to get 3 halves and divide by that new exponent, which gives us a coefficient of 2/3. We are now ready for the final evaluation phase. Following the fundamental theorem of calculus, we substitute our upper limit of 3 and subtract the expression evaluated at a lower limit of 0. This gives us base numbers of 4 and 1. Applying the power of 3 halves means we first take the square root, then cube the result. The square root of 4 is 2, cubed is 8. The square root of 1 is 1, cubed is 1. Multiplying these by 2/3 gives us 16/3 minus 2/3. Our final exact length is 14/3 units. We have successfully measured a bending curve. Now that we have successfully used the formula, let us understand exactly where it comes from. We are going to derive it step by step. We start with the tiny right-angled triangle we saw in our diagram earlier. By the Pythagoras theorem, the length of the tiny segment is the square root of the horizontal change squared plus the vertical change squared. To make this useful for calculus, we use an algebraic trick. We factor out the horizontal change squared. This creates a fraction representing the average slope. Finally, the mean value theorem allows us to replace this average slope with the exact instantaneous derivative at some point C. Continuing our derivation, we now have the length of just one microscopic segment. To find the total length of the entire curve, we must add up all these individual segments using a summation. However, because we are using straight lines to approximate a bending curve, this sum is still only an approximation. To turn this into a perfect, exact measurement, we take a mathematical limit, shrinking the width of our segments down to exactly 0. This limit transforms our massive summation into a precise Riemann integral. And that is how we arrive at our beautiful exact arc length formula. We have done the math, but why does measuring the length of a curve matter in the real world? It turns out this concept is absolutely essential across many fields. If you are an engineer building a massive suspension bridge, you must calculate the exact length of the heavy steel cables hanging in a curved shape to know how much material to manufacture. In physics, calculating the arc length of a winding roller coaster track tells you the exact distance traveled, which is required to find speed and kinetic energy. Even in modern video games, software constantly calculates arc lengths to ensure characters move smoothly along curved paths. Let us summarize what we have learned today. We discovered that arc length is the exact distance measured along a smooth, rectifiable curve. We built our understanding by approximating the curve with tiny straight line segments, relying on the simple Pythagorean theorem. By taking a mathematical limit, we transformed those rough straight line additions into a precise Riemann integral. Finally, we learned that the core formula simply requires us to find the derivative of the curve, square it, add 1, and integrate the square root of that result. You now have the mathematical tools to measure any smooth path, no matter how wildly it bends.